Welcome to NXP's RF Basics training. We've put this slide deck together to brief you upon the basic properties of radio frequency, RF electromagnetic radiation, and the tech lingo that goes along with it. Please bear with us, it's not as bad as it sounds. As we said, in this training block we will do our best to explain the basic elements of RF. This presentation will teach you the most fundamental aspects of RF and where these aspects play fundamental roles. We will start with an introduction on RF as such, and will continue with its fundamental properties such as frequency and wavelength. We'll explain the impressive electromagnetic spectrum, the power that RF can have, the unit decibel, and the term bandwidth of RF applications. We'll zoom into a part of the spectrum and show you some typical applications. And finally, try to impress you with the United States frequency allocation map to give you an idea of RF's ubiquity and importance. What is RF, that we spend so much of our time talking about it and even do business with? RF stands for radio frequency. RF is a form of energy in the modification of time-dependent electronic and magnetic fields. In short, it's an electromagnetic wave, which propagates readily in vacuum, or rather space, or in solid-state media, like metal on a circuit board or through a coaxial cable, or it can propagate out of an antenna into space. In former times, people talked about ether as a medium to carry electromagnetic waves. However, that notion was pretty much wrong. It simply takes space, our three-dimensional world, to carry these types of waves. We said RF is an electromagnetic wave. To be a bit more specific, only the wave frequencies between 1 MHz and 3 GHz are generally called RF. Above 3 GHz up to 30 GHz, we speak about microwaves. Higher frequencies between 30 and 300 GHz are termed millimeter waves. As we will see later when we discuss the electromagnetic spectrum, even higher frequencies manifest themselves as e.g. visible light, or X-rays, or as terahertz body scanners at the airport. This slide will clarify the relation of the terms frequency and wavelength for our electromagnetic RF radiation. Imagine yourself as an observer on the beach. The sea waves pass you by, and you track the distance between them. That's the wavelength. Then you start counting the numbers of waves passing by per minute, say. That would give you the frequency of the sea waves per minute. With our electromagnetic RF waves, it's exactly the same. The number of waves per second is the same as frequency, and the distance between wave maxima is the actual wavelength. If one wave passes each second, this is known as 1 Hz. Very common to RF and microwave are the terms megahertz and gigahertz. This is 1 million and 1 billion waves per second, i.e. the frequency equals 1 MHz and 1 GHz respectively. It's important to note that the speed of electromagnetic waves in vacuum is always the same, regardless of its frequency. The waves travel with the speed of light. If the speed is constant, this also means that higher frequency waves must have smaller wavelength. To give you an idea, your magnetron at home runs at 2.45 GHz frequency, which corresponds to a wavelength of about 12 centimeters. The reciprocal relation between frequency and wavelength is also the fundamental reason that the techniques that engineers use will vary depending on the portion of the RF spectrum they are working with. High-frequency engineers design with components that tend to be smaller, and lower-frequency engineers tend to use physical components that are of larger size. What you see here on this slide is a part of the electromagnetic spectrum visualized. The table shows the frequency range between 10 to the power of 5, 100 kHz, and 10 to the power of 21 Hz, which does not at all imply that it stops at either end. It also relates frequency to other parameters like wavelength, wave number, i.e. waves per centimeter, and electron volt, i.e. the energy of the electromagnetic wave at a given frequency. You should also note that as the frequency increases, more to the right, that the wavelength is dropping, as we said before. You can also see that the higher frequency waves are more energetic by referring to the electron volt scale. Please note the examples of real applications which are shown here as well. On the left, most of the signal transmission kind of applications, electronics, and on the right, the light-based applications or optics can be found. Along with frequency and wavelength, power is another very important parameter to consider. Power is the measure of the energy per unit of time that the electromagnetic wave can deliver. The more power in the wave, the further the wave can be transmitted, like for a broadcast signal, or the more deeply a wave can penetrate, like in certain medical applications. More care must usually be given to systems that operate with more power. It's important to understand power in a relative way. The next slide shows how power and parameters in general can more easily be thought of in relative terms. This slide requires a lot of explanation, but will be key to understanding the material in the more advanced RF courses, so it's important to really understand what's going on here. This slide shows the math tricks and vocabulary used by the engineers. If we go back to all of that forgotten math from our younger years, we remember that instead of multiplying in the linear domain, we can add things in the log domain. Remember? This becomes very useful when numbers become very large, or likewise, very small, and when many multiplications are required. For instance, it becomes much easier to add 5 two-digit numbers than to multiply 5 six-digit numbers. This practice is common when figuring power, gains, and losses through long chains of components. So engineers will always babble in terms of dB, dBm, dBc, etc. To know how many dB some property is, we need to know how many zeros were added to the number in the linear, math domain. Then, to get the number of dBs, we multiply by 10. For instance, if a signal gets amplified and becomes 1,000 times larger, then 3 zeros were added to its value. This 3 gets multiplied by 10 to get 30 dB. Conversely, if a signal becomes 1/1,000,000th as big, it became 10 to the negative 6th power as big, and minus 6 times 10 is minus 60. So in dB, it got affected by minus 60 dB. Some other nice dB number facts to remember are that every doubling of something in the linear domain adds 3 dB in the dB domain. Also, every time something gets cut in half in the linear domain, it drops by 3 dB, or you add minus 3 dB in the dB domain. Likewise, if an amplifier has a gain of 20 dB, it amplifies the signal power by a factor of 100, right? This allows engineers to go through the gains and losses in a system in a very fast way, by adding numbers that are easy to handle. I know this sounds clumsy at first, but after a few years, it's easy to do math in the dB domain, and you become thankful for it. You'll see how this is used in further presentations. The bandwidth of a signal can be considered as the width of the spectral chunk that is being covered by the signal or by the system. For instance, an FM radio can receive waves between 88 and 108 MHz. The car receiver then has a 20 MHz bandwidth. The FM wave per radio station itself has a certain bandwidth as well, which indicates how much information the wave can carry. So, your favorite FM station transmits a wave that is about 200 kHz wide. The music only covers a chunk around 20 kHz wide. So the engineers used the remaining frequency space in that 200 kHz to pack information onto the wave to help the transmission be more pure, and to let your car navigation system know where not to go. This same principle applies to all the RF and microwave applications, and scales in complexity as the system needs become more stringent. For example, in highly complex third-generation cellular environments, system needs far exceed those of music transmission for FM. This is why cellular bands operate over broader bandwidths, and each transmission from the cell towers is more broadband than for FM transmission. The ever-increasing need for information transmission usually adds to the demands placed on the electronic components, and is the source of many of the challenges for today's engineers, and in fact, fuels a large part of our HPRF business. This table shows a few frequency blocks used by most popular applications. In general, systems that demand larger transmission distance will tend to be granted lower frequency allocations. That's because using lower frequencies has a physical advantage of having less degradation caused by obstacles. You'll also see 4 ISM bands called out. These are bands that are free to use with certain maximum power limitations. The industrial, scientific, and medical ISM radio bands were originally reserved internationally for the use of RF electromagnetic fields for industrial, scientific, and medical purposes other than communications. You will again recognize your magnetron's frequency is an ISM band, together with your WLAN. In general, communications equipment must accept any interference generated by ISM equipment. The bands and applications up to 3.8 GHz are covered by products from RF Power. Likewise, the RF small signal portfolio covers even higher frequencies and applications up to and above 40 GHz. There are, of course, more bands defined at higher frequencies. See earlier electromagnetic wave spectrum. These frequencies are also used for several applications, but can only be served using other technologies than the ones used currently by RF Power and RF Small Signal. This slide is just meant to illustrate how complex and diverse the usage of electromagnetic spectrum has become nowadays. It is a scheme the U.S. government, the FCC, has come up with to allocate the overall spectrum to several licensed, unlicensed, or government-only use. Per line, it gives a part of the overall spectrum. In total, it ranges between 3 kHz and 300 GHz. RF and microwave engineers only have a few small frequency slices available to them depending on the application. In other countries, this allocation might look very different. That's also why there's not just one single frequency in the world to do all the cellular telephones with. In fact, all countries in the world work together in the ITU body to align the frequency use across borders. The electromagnetic waves would not just stop there. This also finishes the presentation on RF basics. We hope it is clear and understandable so that you now have an idea what RF and its associated applications are all about.